Ever wondered what fuels our world, from the car you drive to the plastics all around us? It all comes down to a fundamental class of organic compounds, hydrocarbons. Welcome to the Deep Dive, your shortcut to mastering core concepts. Today, we're embarking on a focused deep dive into hydrocarbons, a critical unit for your Class 11 and 12 board exams, and definitely a high-scoring topic for competitive exams like ARE and NEET. You've shared your notes and textbook excerpts, and our mission today is to systematically break down this complex unit. We'll navigate through the classifications, structures, preparation methods, properties, and reactions of alkenes, alkynes, and aromatic compounds. We'll also touch upon crucial aspects like isomerism and the real-world impact of these compounds. Get ready for a targeted, exam-oriented learning experience.
Thank you for joining us today. We're really eager to unravel the world of hydrocarbons. To begin, could you perhaps explain what exactly hydrocarbons are and why they hold such immense importance in our daily lives?
Absolutely. The term hydrocarbon itself is quite descriptive. These are organic compounds composed solely of carbon and hydrogen atoms. While they are the simplest organic compounds in terms of elemental composition, their role in our modern world is anything but simple. It's, immensely significant and pervasive. They are truly the backbone of our energy consumption and a fundamental building block for countless materials. When we discuss the importance of hydrocarbons, we're essentially talking about their ubiquitous presence as both primary energy sources and vital industrial raw materials. Let's consider some common examples you encounter every single day. For energy, think about the fuels that power homes and transport. Liquefied petroleum gas, or LPG, that's a common domestic fuel, valued for its efficient burning and relatively low pollution. Then we have compressed natural gas, CNG, and liquefied natural gas, LNG, widely adopted as cleaner automotive and industrial fuels, especially in our metro cities. These are often preferred over petrol and diesel in many applications due to their lower environmental impact. Petrol, diesel, and kerosene are other common liquid fuels, all derived from crude petroleum through a process called fractional distillation. This industrial separation technique allows us to isolate different hydrocarbon mixtures based on their boiling points. Kerosene, while still used domestically, is known to produce more pollution compared to LPG. We also get coal gas for the destructive distillation of coal, and natural gas is often found alongside petroleum deposits, which can be compressed into CNG. So whether it's powering your vehicle, heating your home, or fueling industrial processes, hydrocarbons are the indispensable primary sources of energy driving our global economy. But the utility extends far beyond just fuels. Hydrocarbons are indispensable starting materials for the manufacture of an incredible range of everyday products. Think of the plastics that are so integral to our lives. Polythene, polypropylene, polystyrene, these widely used polymers all originate from simpler alkene hydrocarbon molecules. Beyond plastics, higher hydrocarbons serve as excellent solvents for paints, ensuring smooth application and drying. And for those of you considering careers in pharmaceuticals or textiles, remember that hydrocarbons form the foundational compounds for synthesizing numerous dyes and drugs. So from the smallest plastic toy to essential medicines and massive power plants, hydrocarbons are central to virtually every aspect of modern life. Their study is not just academic, it's about understanding the very fabric of our technological world.
That truly highlights their undeniable importance. It's clear they are not just abstract chemical concepts, but fundamental to our daily existence. Given such diverse applications, how are these varied hydrocarbons actually categorized? Could you walk us through their main classifications, which I understand is a foundational concept for our exams?
Certainly. Understanding the classification of hydrocarbons is indeed fundamental for conceptual clarity, especially for those competitive exams. They are broadly categorized into three main types based on the kinds of carbon-carbon bonds present within their molecular structures. Let's delve into each category. First, we have saturated hydrocarbons. The term saturated here signifies that these compounds contain only carbon-carbon single bonds and carbon-hydrogen single bonds. Crucially, they lack any double or triple bonds. Within this category, we distinguish two main types. Alkenes. These are characterized by open-chain structures. Imagine a continuous chain of carbon atoms, or a branched tree-like arrangement where all carbons are joined exclusively by single bonds. You might recall studying some basics of these in earlier chapters, right? Cycloalkanes. These are also saturated, meaning they only contain single bonds, but instead of an open chain, their carbon atoms form a closed ring structure. Think of alkenes like a simple flexible chain where every link is single. Cycloalkanes are similar, but the chain bends and connects back to itself, forming a ring, yet all the links remain single. This distinction is vital. Next, we move to unsaturated hydrocarbons. As the name suggests, these compounds are not saturated with hydrogen atoms because they contain at least one carbon-carbon multiple bond. This means their structure will feature either double bonds or triple bonds, or sometimes both. Compounds containing carbon-carbon double bonds are known as alkenes, and compounds containing carbon-carbon triple bonds are called alkenes. Finally, we have aromatic hydrocarbons. These constitute a special and very distinct class of cyclic compounds. They exhibit a unique kind of enhanced stability due to electron delocalization and possess characteristic chemical properties that clearly differentiate them from simple cyclic alkenes or alkanes. We'll thoroughly explore this unique characteristic, known as aromaticity and Hückel's rule, in detail later in our discussion. For now, you can consider these as the VIPs of the hydrocarbon family, with their own unique set of rules. While we're on the topic of structures, remember that visualizing these molecules in 3D can significantly aid your understanding. For simple alkenes, you can use basic models like toothpicks for bonds and plasticine balls for atoms. For molecules with multiple bonds or complex cyclic structures, specific spring models or software visualization tools can be very helpful to grasp their fixed geometries.
That's a very clear and well-structured classification, providing a perfect roadmap for what's to come. Let's begin our deep dive into the first category, alkenes. Could you walk us through their fundamental characteristic features and then guide us on how we systematically name them for exams?
Right. Alkanes are indeed the simplest members of the saturated open-chain hydrocarbons, defined by the exclusive presence of carbon-carbon single bonds. The most basic and foundational molecule in this family is methane, CH4, a gas you might encounter in places like natural gas deposits or marshy areas. When we study organic chemistry, we often talk about a homologous series. This is basically a series of compounds where successive members differ by a nuclear CH2 group. For alkanes, if you theoretically replace one hydrogen of methane with a nuclear CH3 group, you get C2H6, which is ethane. Continuing this, we get C3H8 propane, C4H10 butane, and so on. This systematic pattern allows us to derive a very important general formula for alkanes, CnH2n plus 2. Here n represents the number of carbon atoms. This formula is absolutely vital for competitive exams. It helps you quickly determine the molecular formula of any alkane or deduce the number of carbons given the formula. Let's quickly revisit the structure of methane, which is a common foundational question. Based on the VSE pair theory, methane adopts a tetrahedral structure. Imagine the carbon atom at the exact center, with its 4 hydrogen atoms positioned at the 4 corners of a regular tetrahedron. This arrangement dictates that all the HCH bond angles are precisely at 109.5 degrees. In terms of typical bond characteristics within alkanes, the carbon-carbon see the single bond length is about 154 picometers, and the carbon-hydrogen CH bond length is around 112 picometers. These bonds are formed by the head-on overlapping of sp3 hybrid orbitals from carbon, with either another sp3 orbital from an adjacent carbon, or the one's orbitals of hydrogen, forming strong sigma bonds. A key characteristic of alkanes fundamental to their chemical behavior is their relative inertness. Under normal conditions, they don't readily react with common reagents like acids, bases, or most oxidizing and reducing agents. This stability is why they were historically known as paraffins, derived from the Latin param affinis, meaning little affinity or low reactivity. This explains why they are used as protective layers or stable solvents.
That's fascinating. So their very simple structure dictates this inertness. This foundational understanding is certainly key for cracking conceptual questions in exams. Now let's move to a crucial section for any competitive exam aspirant. Nomenclature and isomerism in alkanes. This is where many students can gain valuable marks or unfortunately lose them.
You're absolutely right. Mastering nomenclature and isomerism is non-negotiable for competitive exams. While simple alkanes like methane, ethane, and propane have only one possible structural arrangement, higher alkanes exhibit isomerism. We'll focus on structural isomerism, and specifically chain isomerism, which is very common here. Let's illustrate with butane, C4H10. You can arrange these 4 carbon atoms in 2 distinct ways, leading to 2 chain isomers. First, N-butane, a continuous straight chain. Second, 2-methylpropane, or you might know it as isobutane, a branch structure where 3 carbons form a chain and the 4th is a branch. These 2 compounds have the identical molecular formula, C4H10, but different arrangements of atoms, resulting in different physical properties like boiling points. This difference in carbon backbone defines chain isomerism. For pentane, C5H12, you can systematically derive 3 chain isomers, N-pentane, 2-methylbutane, and 2,2-dimethylpropane. As the number of carbons increases, the number of possible chain isomers grows dramatically.
Before we practice naming, it's vital to classify carbon atoms in an alkane chain based on the number of other carbons they're directly bonded to. A primary 1-degree carbon is attached to at most 1 other carbon atom. Terminal carbons are always primary. A secondary 2-degree carbon is attached to 2 other carbon atoms. A tertiary 3 degrees carbon is attached to 3 other carbon atoms. And a quaternary 4 degrees carbon is attached to 4 other carbon atoms. Identifying these types is crucial for understanding reaction mechanisms later on. Okay, let's apply this to a common exam problem. Problem 9.1 asks you to write structures of different chain isomers for C6H14 and their IUPAC names. For C6H14, there are precisely 5 chain isomers. To find them systematically, here's the approach. First, start with the longest possible continuous chain, 6 carbons. That gives you unhexane. Simple enough. Second, reduce the main chain by 1 carbon, so make it 5 carbons long, and use the remaining carbon as a methyl branch. Place this branch at different positions, but be careful not to create duplicate structures. This gives 2-methylpentane and 3-methylpentane.
Finally, reduce the main chain further down to 4 carbons and use the remaining 2 carbons as methyl branches. You can place them at positions like 2-pas-3-dimethyl or 2-methyl-2-dimethyl. This yields 2-pas-3-dimethylbutane and 2-pas-2-dimethylbutane. This systematic approach ensures you don't miss any isomers, which is really key for a numerical problem in the exams. Now, an alkyl group is essentially an alkane with 1 hydrogen atom removed. It's represented by the general formula CnH2n+1. For instance, methyl-CH3 for methane, or ethyl-T2H5 from ethane. Problem 9.2 in your textbook asks you to derive all 8 isomeric alkyl groups for C5H11 and name the corresponding alcohols. This is a great practice problem that tests both isomer generation and IUPAC naming. The key is to draw all possible carbon backbones first, then systematically remove a hydrogen from each unique position. To recap the IUPAC nomenclature rules for substituted alkanes, always remember the sequence. 1. Identify the longest continuous carbon chain. This is your parent alkane. 2. Number the chain to give the lowest possible set of numbers to the substituents. If there's a tie, prioritize the substituent that comes first alphabetically. 3.
Name substituents and list them alphabetically with their position numbers. Remember, prefixes like "-" "tri" are ignored for alphabetical order, but complex prefixes like iso or tert are included. 4. Finally, derive the correct structure from an IUPAC name by first drawing the parent chain, then numbering it, attaching substituents, and finally adding hydrogens to satisfy valency. This methodical approach will prevent mistakes in exams. Let's quickly highlight a common pitfall from problem 9.5, identifying incorrect IUPAC names. For example, 2-ethylpentane is an incorrect name. Why? Because when you draw it out, you realize the longest continuous carbon chain is actually 6 carbons, not 5. The ethyl group is part of a longer chain, making the correct name 3-methylhexane. Similarly, 5-ethyl-3-methylheptane is incorrect, because the numbering priority should give the alphabetically preferred ethyl group the lower number, making the correct name 3-ethyl-5-methylheptane. These problems are designed to test your thoroughness in applying the rules, so pay close attention to selecting the longest chain and correct numbering. It's a common area where marks are lost.
These naming exercises are indeed invaluable for exam success, as they test both recall and systematic application. Now that we've covered their structure and naming, how are alkanes actually prepared for practical and industrial uses?
Well, while petroleum and natural gas are the primary natural sources of alkanes, for laboratory synthesis and specific industrial applications, we have several well-defined methods. Let's look at the key preparation methods. 1. From unsaturated hydrocarbons, hydrogenation. This involves adding dihydrogen gas H2 to alkenes or alkenes. The conditions are important. Requires catalysts like finely divided platinum, palladium, or nickel. PNE and PA work at room temperature, while ME needs higher temperatures and pressures. The outcome. It saturates the multiple bonds to form single bonds, yielding alkanes. For instance, ethene, CH2CH2 becomes ethene, CH3CH3, and propane, CH3CH2 becomes propane, CH3CH2CH3, by adding 2 molecules of H2. This is a very clean conversion. 2. From alkyl halides. Alkyl halides can be reduced to alkenes in 2 main ways. First one, reduction with zinc and dilute HCl. Most alkyl halides, except fluorides, can be reduced to alkenes. For example, chloromethane CH3Cl becomes methane, CH4. Straightforward. Second, 2-Wurtz reaction. This is a famous named reaction, very important for exams, used for preparing higher alkanes with an even number of carbon atoms. An alkyl halide reacts with sodium metal in dry ether. Now here's the key insight. While effective, it's generally not preferred for preparing alkanes with an odd number of carbon atoms. Why? If you use 2 different alkyl halide, say bromomethane and bromethane, you will inevitably get a mixture of 3 alkanes. Ethane from 2 bromophanes, butanes from 2 bromophanes, and propane for 1 of each. Separating this mixture is extremely difficult and inefficient, making it impractical. This is a frequent trick question in exams, so watch out for it. 3. From carboxylic acids. 2 important methods here. First, decarboxylation, heating the sodium salt of a carboxylic acid with soda lime, which is a mixture of NaOH plus CaO. The key outcome here is that this method produces an alkane with 1 carbon atom less than the original carboxylic acid. For example, sodium ethanoate, which has 2 carbons, gives methane, which has 1 carbon. So if you need propane, 3 carbons, you start with sodium pentanoate, 4 carbons, right? Second, Kolbe's electrolytic method. This involves the electrolysis of an aqueous solution of a sodium or potassium salt over carboxylic acid. The key outcome here is different. This method exclusively yields alkanes with an even number of carbon atoms at the anode. For example, sodium acetate produces ethane. Okay, let's briefly touch upon the mechanism concept here because it explains the outcome. It involves a free radical process. First, the carboxylate ion loses an electron at the anode to form a free radical. This radical then quickly loses a CO2 molecule, forming an alkyl-free radical. 2 of these alkyl-free radicals then combine to form the alkane. And this leads to a crucial consideration. This mechanism explained why methane cannot be prepared by Kolbe's electrolytic method. Since the process involves the combination of 2 alkyl radicals, the smallest alkane you can form is ethane, from 2 methyl radicals combining. You simply can't form methane this way. This is a common reasoning question in competitive exams.
That's a thorough overview of preparation methods. The nuances of Kolbe's and Wurtz reactions, especially regarding the number of carbons, are definitely critical for exam performance. Now let's explore their general physical and chemical behaviors.
Right. Understanding the properties of alkanes helps us predict their behavior and differentiate them, which is essential for problem solving in exams. Let's look at their physical properties first. Polarity. Alkanes are considered almost nonpolar. This is due to the very small electronegativity difference between carbon and hydrogen. Because they're nonpolar, they only have weak intermolecular forces, specifically van der Waals forces, stayed at room temperature. These weak forces has consequences. C1 to C4 alkanes are gases, think methane, propane in your LPG cylinders. C5 to C17 are liquids, like the components of petrol, and C18 and higher are solids, like paraffin wax. Solubility. Being nonpolar, they are insoluble in water, which is polar, remember, like dissolves like. They are hydrophobic, but they are soluble in nonpolar organic solvents. Think of how petrol, a hydrocarbon mixture, is used for dry cleaning grease. It dissolves the nonpolar grease. Now for a frequently tested concept, boiling point. This is a steady increase in boiling point with increasing molecular mass. And this makes sense, right? Larger molecules have more electrons, larger surface area, leading to stronger van der Waals forces between them. More energy is needed to overcome these stronger forces. But here's a key point, the effective branching on boiling point. This is a common trick question. Among isomers, which have the same molecular formula, straight-chain alkanes have higher boiling points than their branched isomers. Why? Well, branching makes the molecule more compact, more spherical. This reduces the effective surface area for intermolecular contact. Less surface contact means weaker van der Waals forces, which are overcome at lower temperatures. For example, look at the isomers of pentane in Table 9.2. And pentane, straight chain, boils at 309.1 K, while the highly branched 2-carbon-2-dimethylpropane boils much lower at 282.5 K. It's a very important distinction for multiple choice questions. Okay, moving to their chemical properties. Despite being generally inert, remember the paraffin name, alkenes do undergo specific reactions, but usually under certain forcing conditions. 1. Substitution reactions. This is their most characteristic reaction. Hydrogen atoms are replaced by other atoms or groups, typically halogens. Conditions are important. High temperature, around 573-773 K, or diffuse sunlight. UV light is usually needed for halogenation. Take the chlorination of methane as an example. This is a sequential substitution. It doesn't stop neatly after one hydrogen is replaced. It can proceed further to form chloromethane, then dichloromethane, then chloroform, and finally carbon tetrachloride. You usually end up with a mixture of products. The reactivity order is also important. For halogens, it's F2, Cl2, Br2, I2. Fluorine is violently reactive. Iodine is very slow and reversible. For hydrogen replacement, tertiary, 3 degrees hydrogens are replaced more easily than secondary, 2 degrees, which are easier than primary, 1 degrees. Now, let's break down the free radical chain mechanism of halogenation. This is critical for NEET. Think of it like a chain reaction or a relay race with 3 distinct phases. First, initiation. Light or heat provides the energy to break the halogen molecule, like Cl2, evenly. This is called homolysis, forming highly reactive free radicals, like 2Cl radicals. These are the starters of the race. Second, 2, propagation. This is where the chain reaction keeps going. A chlorine radical attacks a methane molecule, grabs a hydrogen atom to form HCl, and leaves behind a methyl radical, CH3. This methyl radical then attacks another Cl2 molecule, forming the product, CH3Cl, and regenerating a chlorine radical, Cl. This new Cl can then attack another methane molecule, and the cycle continues, propagating the chain. This phase explains why a small amount of initial radicals can lead to a large amount of product. It also explains how further substitution occurs. For example, Cl attacking CH3Cl. Third, 3, termination. The chain reaction eventually stops when 2 radicals collide and combine, effectively removing reactive species from the cycle. This could be two Cl radicals forming Cl2, two CH3 radicals forming ethane, CH3CH3 explaining this common byproduct, or a CH3 and a Cl forming CH3Cl. Understanding these three phases, initiation, propagation, termination, helps predict reaction outcomes and byproducts. 2. Combustion. Alkenes are excellent fuels. They undergo complete oxidation and sufficient oxygen to produce CO2 and H2O, releasing a large amount of heat. It's an exothermic reaction. That's why methane, natural gas, or LPG are used as fuels. If combustion is incomplete, meaning there's insufficient oxygen, you get carbon monoxide, CO, or even carbon black, so instead of CO2. Carbon black is used in ink and pigments. 3. Controlled oxidation. Under specific conditions, with regulated oxygen supply and specific catalysts, alkanes can be partially oxidized to useful products like alcohols, for example, methane to methanol using a Q catalyst, aldehydes, or carboxylic acids. This is very important for industrial synthesis. 4. Isomerization. When you heat alkanes with anhydrous LCl3 and HCl gas, they can rearrange their carbon skeleton to form branched chain isomers. For example, N-hexane can isomerize to 2-methylpentane and 3-methylpentane. This is used industrially to improve the quality of gasoline, increases octane number. 5. Aromatization, also called reforming. This is a really interesting one. N-alkanes with 6 or more carbon atoms, when heated to high temperatures around 773 K and pressures over specific catalysts like oxides of vanadium, molybdenum, or chromium on alumina support, can lose hydrogen and cyclize to form aromatic compounds like benzene and its derivatives. For example, N-hexane yields benzene. This is a crucial industrial process for producing aromatic feedstocks. 6. Reaction with steam. Methane reacts with steam at very high temperatures, 1273 K, using a nickel catalyst to produce carbon monoxide and hydrogen gas, H2. This mixture is called synthesis gas and is an important industrial method for preparing dihydrogen gas. 7. Pyrolysis, or cracking. This is the thermal decomposition of higher alkanes into smaller, more useful fragments, lower alkanes, by applying heat. It typically proceeds via a free radical mechanism. This is vital in the petroleum industry to break down large, less valuable hydrocarbon molecules into smaller ones suitable for gasoline, petrol, or as chemical feedstocks. For example, dodecane C12 might crack into heptane and pentene C5.
That's an exhaustive list of reactions. The free radical mechanism for halogenation and the various controlled oxidation products are particularly important for exams, as you mentioned. Now, let's explore a very interesting concept related to alkane flexibility. Conformations. This often comes up in stereochemistry questions, right?
Yes, absolutely. Let's delve into conformations, a concept that arises because of the nature of single bonds, particularly in alkenes. Alkenes contain carbon sigma. A key feature of sigma bonds is that there's essentially free rotation around the CC single bond axis. Imagine twisting one end of the molecule relative to the other. This rotation allows the molecule to adopt different three-dimensional spatial arrangements of its atoms. These different arrangements, which can be interconverted simply by rotation around single bonds, are called conformations, or sometimes conformers or rotamers. Now, while we say free rotation, it isn't entirely free. There's a small energy barrier involved. This is due to weak repulsive interactions between the electron clouds of adjacent bonds. We call this small energy barrier torsional strain. To understand this better, let's focus on the simplest alkane that shows this phenomenon, ethane, C2H6. It has one CC single bond connecting two methyl groups. If you imagine rotating one methyl group relative to the other around the CC bond, you can visualize an infinite number of possible conformations. However, we usually focus on two extreme and most significant conformations. First, the eclipsed conformation. In this arrangement, if you look down the CC bond, the hydrogen atoms on the front carbon are directly aligned with or eclipsing the hydrogen atoms on the rear carbon. They are as close as possible in this view. Second, the staggered conformation. Here, the hydrogen atoms on the front carbon are positioned exactly in the gaps between the hydrogen atoms on the rear carbon. They are as far apart as possible, minimizing repulsion. Any intermediate conformation between these two extremes is called a skew conformation. Okay, visualizing these is crucial for exams. You must be able to draw and interpret these using specific projection methods. Please refer to figures 9.2 and 9.3 in your textbook as I describe these. One is sawhorse projections. Imagine you're viewing the CC bond from an oblique angle, slightly from above and the side. The CC bond is drawn as a diagonal line. The front carbon is usually shown at the lower end, the rear carbon at the upper end. Lines radiate from each carbon to represent the CH bonds. You can draw both eclipsed, where the front and back CH bonds appear aligned, and staggered, where they appear maximally separated. The other, very common in competitive exams, is Newman projections, figure 9.3. Here you view the molecule directly head-on, looking straight down the CC bond axis. The front carbon atom is represented by a point, the junction of 3 bonds. The 3 CH bonds attached to it radiate from this point at 120 degrees. The rear carbon atom is represented by a circle behind the point. The 3 CH bonds attached to the rear carbon are shown as shorter lines coming out from the edge of the circle. This projection very clearly depicts the eclipsed conformation, where the front and back hydrogens align perfectly, and the staggered conformation, where the front hydrogens are in the dihedral angle gaps of the back hydrogens. Practice drawing these projections. They are very important. Now let's talk about the stability of conformations. This is highly testable. The staggered form is more stable and is the preferred conformation. Why? Simple. The electron clouds of the CH bonds on the adjacent carbons are farthest apart in this arrangement. This leads to minimum repulsive forces between them, and therefore minimum energy and maximum stability. Conversely, the eclipsed form is less stable. The electron clouds of the CH bonds are forced closer together, resulting in increased electron repulsion. This is the torsional strain, higher energy, and thus lesser stability. The energy difference between the staggered and eclipsed forms in ethane is quite small, only about 12.5 kilojmol. This small energy barrier means that at ordinary room temperatures, the molecules have enough thermal energy to rapidly rotate and interconvert between conformations millions of times per second. Because of this rapid interconversion, it's impossible to isolate pure eclipsed or staggered conformers of ethane at room temperature.
The concept of conformations and their stability, especially using Sawhorse and Newman projections, is definitely a favorite for exam setters, testing visualization skills. Now let's shift our focus to the next class of hydrocarbons, alkenes, characterized by their carbon-carbon double bonds.
Right, alkenes. These are unsaturated hydrocarbons defined by the presence of at least one carbon-carbon double bond. Because of this double bond, they have 2 fewer hydrogen atoms compared to the corresponding alkane with the same number of carbons. Their general formula is CnH2n. They are also historically known as olefins, which means oil forming. This name came about because the simplest alkene, ethene, C2H4, was observed to form an oily liquid when it reacted with chlorine gas. Understanding the structure of the double bond is absolutely fundamental to understanding alkene chemistry and reactivity. A carbon-carbon double bond is not just 2 single bonds. It consists of 1 strong sigma, formed by the head-on overlap of septupido hybridized orbitals, and 1 weaker pi. This pi bond is formed by the lateral or sideways overlap of the unhybridized 2p orbitals on each carbon. Now this pi bond is the key. Being weaker and formed by sideways overlap, its electrons are loosely held and more exposed, more mobile, above and below the plane of the sigma bond. This makes the double bond region electron-rich. Consequently, alkanes act as sources of electron density and are highly susceptible to attack by electrophilic reagents, species that are seeking electrons. This weaker pi bond is what makes alkanes much more reactive than alkenes, and why they readily undergo addition reactions, where the pi bond breaks and new sigma bonds are formed. Also, the C2C double bond length, about 134 pm, is significantly shorter than a CC single bond, 154 pm. Okay, for IUPAC nomenclature of alkenes, remember these key rules. 1. Select the longest continuous carbon chain that contains the double bond. This is the parent chain. 2. Number the chain starting from the end that is nearer to the double bond, giving the double bond carbons the lowest possible numbers. 3. Replace the alkane suffix -ane with -ane. Indicate the position of the double bond using the number of the first carbon atom of the double bond. Ethene, C2H4, is the first stable member. Examples include propene, but 1 alkane and but 2 entyl. Problem 9.7 and 9.8 in your textbook are excellent practice for naming alkenes and counting the number of sigma and pi bonds within them. Remember, a double bond contains 1 sigma and 1 pi bond. Practice these systematically.
Nomenclature and understanding bond types are indeed fundamental for competitive exams. What about isomerism in alkenes? Does the double bond introduce new types of isomerism beyond what we saw in alkenes?
Yes, it absolutely does. Alkanes are particularly interesting in this regard. They exhibit structural isomerism, just like alkanes, but they also show a very important type of stereoisomerism called geometrical isomerism, which is often referred to as cis-trans isomerism. This is a highly tested concept in exams. First, let's quickly touch upon structural isomerism. We saw chain and position isomerism in alkanes. It's similar for alkenes, for example, with C4H8, but 1 and 8 and but 2 N are position isomers, differing in the position of the double bond. But 1-ane and 2-methylprop-1 are chain isomers, differing in the carbon skeleton. Problem 9.9 asks for all structural isomers of the alkane C5H10. There are 5 such isomers. The strategy is similar to finding alkane isomers. First, draw the straight chain isomers varying the double bond position, pent1, pentecta1. Then consider branched chains, a 4-carbon chain with the methyl branch, and place the double bond in possible positions, 2-methyl but 1-ane, 3-methyl but 1-ane, 2-methyl but 2-ane. Systematically drawing these will help you identify all of them without duplication. Now, for the really important part, geometrical isomerism, cis-trans isomerism. This arises specifically because of the restricted rotation around the carbon double bond. Unlike a single bond, which allows free rotation, the presence of the pi bond in a double bond prevents the atoms from rotating freely around the bond axis. Think of it like two pieces of cardboard joined by two nails instead of one. You can't twist one relative to the other easily. For cis-trans isomerism to occur, there's a crucial condition. Each of the doubly bonded carbon atoms must be attached to two different atoms or groups. Let's say the double bond is CC. If carbon 1 has groups A and B and carbon 2 has groups X and Y, then A must be different from B, A and X must be different from Y. If any one carbon of the double bond has two identical groups attached, example CH2CBr2, where the first carbon has two identical H atoms, then it cannot show cis-trans isomerism. If the condition is met, we have two possibilities. The cis isomer, where identical or similar groups are on the same side of the imaginary plane cutting through the double bond. The trans isomer, where identical or similar groups are on opposite sides of the double bond. These cis and trans isomers are stereoisomers. They have the same connectivity but differ in the spatial arrangement of atoms. This difference in spatial arrangement leads to real differences in their physical properties, such as melting point, boiling point, solubility, and, importantly, dipole moment. Let's take but-2-enene as a classic example. Each double-bonded carbon is attached to a hydrogen and a methyl group, so the condition is met. In cis-but-2, both methyl groups and both hydrogens are on the same side. The CCH3 bond dipoles add up vectorially, resulting in a net dipole moment, about 0.33 DeV, making this as isomer polar. In trans-but-2-ene, the methyl groups are on opposite sides. The bond dipoles are equal and opposite, so they cancel each other out, resulting in a zero or near-zero net dipole moment. The trans isomer is nonpolar. This difference in polarity is a very frequent exam question and affects properties like boiling point. Generally, the trans isomer, being more symmetrical, packs better in the solid state and often has a higher melting point. Problem 9.NESO 9.11 in your textbook provide excellent practice for identifying which molecules can exhibit cis-trans isomerism and for drawing the respective isomers. Remember to always check the two different groups on each carbon condition carefully.
Geometrical isomerism is certainly a crucial topic for distinguishing compounds and understanding their properties. Now that we understand the double bond structure and its impact on isomerism, how do we prepare these double bonded compounds in the lab or industry?
Right, preparing alkenes involves several important reactions, and the specific conditions and reagents used are often tested in competitive exams, so pay close attention here. Let's detail the main methods. 1. From alkenes, partial reduction. You can convert a triple bond to a double bond by carefully controlled addition of hydrogen. To obtain cis-alkenes, you need to perform partial reduction using dihydrogen gas, H2, in the presence of a special catalyst called Lindlar's catalyst. This is typically palladium deposited on calcium carbonate, which has been poisoned or partially deactivated with substances like sulfur compounds or quinoline. This poisoning prevents the reaction from going all the way to the alkene and ensures syn addition. Both hydrogens add from the same side of the triple bond, leading to the cis product. To obtain transalkenes, you use a different method reduction with sodium metal dissolved in liquid ammonia. This proceeds via a different mechanism involving electron transfer and results in anti-addition. Hydrogens add from opposite sides, leading to the trans product. An important note, if you prepare propene this way, from propine, it will not show geometrical isomerism because one of its double bonded carbons, the terminal CH2, has two identical hydrogen atoms, failing the condition. 2. From alkyl halides, dehydrohalogenation, Bay elimination. This is a very common method. You heat an alkyl halide with a strong base, typically alcoholic potash, KOH dissolved in ethanol. The base removes a proton, H+, from the carbon atom beta to the halogen, the big carbon, and the halogen atom leaves from the alpha carbon, H. This simultaneous removal of H and X leads to the formation of a double bond. It's called Bay elimination because the hydrogen is removed from the beta position. The ease of this reaction depends on the alkyl halide. Tertiary halides react fastest, followed by secondary, then primary. Also, alkyl iodides react faster than bromides, which are faster than chlorides. 3. From vicinal dehalides, dehalogenation. Vicinal dehalides are compounds with halogen atoms on adjacent carbon atoms. When these are treated with zinc metal, usually in an alcoholic solvent, the zinc removes both halogen atoms, forming a zinc dihalide, like ZnBr2, and generating an alkene double bond between the adjacent carbons. For example, 1,2-D-bromothane reacts with zinc diethane. 4. From alcohols by acidic dehydration. Heating an alcohol with a strong dehydrating acid, typically concentrated sulfuric acid, H2SO4, or sometimes phosphoric acid, H3PO4, leads to the elimination of a water molecule, forming an alkene. This is also a type of Weil elimination reaction, where an H from the beta carbon and the OH group from the alpha carbon are removed. For example, ethanol, when heated with concentrated H2SO4, yields ethene and water.
These preparation methods, especially remembering the specific conditions like Lindlar's catalyst for cis-alkynes or alcoholic KOH for elimination, are indeed critical for exams. Now, let's explore how alkenes react, particularly given the reactivity of their double bond.
Exactly. Alkanes share some physical properties with alkanes, for instance. Their boiling points generally increase with molecular size. However, their chemical behavior is drastically different. Their defining characteristic lies in the presence of those loosely held pi electrons in the double bond. This makes them electron-rich and thus highly reactive, especially towards electrophilic addition reactions. This is the key theme for alkene reactions. Let's focus on their main chemical properties. 1. Addition of dihydrogen, hydrogenation. We already saw this when preparing alkanes. Adding H2 across the double bond in the presence of catalysts like PDE, or Ni converts alkanes to the corresponding alkanes. 2. Addition of halogens, halogation. Halogens like chlorine, Cl2, and bromine, Br2, readily add across the double bond to form vicinal dihalides, halogens on adjacent carbons. Iodine usually reacts much more slowly or not at all under normal conditions. Now, this reaction with bromine is particularly important because it serves as a test for unsaturation. Bromine, dissolved in an inert solvent like carbon tetrachloride, CCl4, has a distinct reddish-orange color. When this solution is added to an alkene, or alkene, the bromine rapidly adds across the multiple bond and the color disappears or is discharged. This decolorization is a classic qualitative test indicating the presence of a double or triple bond in an unknown organic compound. For example, ethene plus Br2 in CCl4, 1-Gur2 dibromethane, colorless. The mechanism is electrophilic addition, often involving a silicon ion intermediate. 3. Addition of hydrogen halides, hydrophilogenation. Hydrogen halides HCl, HBr, HI add across a double bond to form alkyl halides. The reactivity order is HI, HBr, HCl, reflecting the bond strength of HX. HI is weakest, easiest to break. Now, for addition to unsymmetric alkenes, we encounter two extremely important concepts for your competitive exams: Markovnikov's rule and the anti-Markovnikov rule, peroxide effect. You absolutely must master these. Let's start with Markovnikov's rule. This rule predicts the regiochemistry where the H and X add for the addition of HX to an unsymmetrical alkane, an alkene where the two carbons of the double bond have different numbers of hydrogens attached. The rule states, when an unsymmetrical reagent, like HBr, adds to an unsymmetrical alkene, the negative part of the addendum, the adding molecule, for example, Br and HBr, attaches to the carbon atom of the double bond which possesses the fewer number of hydrogen atoms. The positive part, H+, goes to the carbon with more hydrogens. Let's take the example of HBr adding to propene, CH3, CH2. The middle carbon, CH, has one hydrogen, while the terminal carbon, CH2, has two hydrogens. According to Markovnikov's rule, the negative part, Br, will go to the middle carbon, fewer hydrogens, and the H+ will go to the terminal carbon. The major product formed is therefore 2-bromopropane, CH3-CHBr-CH3. Okay, why does this happen? The underlying reason is the stability of the carbocation intermediate formed during the reaction mechanism. Let's break it down step by step. First, the electrophile, H plus C, attacks the pi electrons of the double bond. This can happen in two ways for propene. If H+ adds to the terminal carbon, CH2, it forms a secondary carbocation, CH3, CH3, CH plus CH3. If H+ adds to the middle carbon, CH, it forms a primary carbocation, CH3, CH2, CH2+. Now, we know from carbocation stability rules that secondary carbocations are much more stable than primary carbocations due to hyperconjugation and inductive effects. Since the formation of the more stable intermediate is faster, the reaction proceeds preferentially via the secondary carbocation. In the second step, the nucleophile, Br, attacks this more stable secondary carbocation to give the final product, 2-bromopropane. So Markovnikov's rule is essentially a consequence of forming the most stable carbocation intermediate. This principle is central to many organic reactions. Now, for the flip side, anti-Markovnikov addition, also known as the peroxide effect or the Karash effect. This is equally important, often tested alongside Markovnikov's rule. Pay close attention to the conditions. This effect occurs only with HBr, it does not happen with HCl or HI, and only when the reaction is carried out in the presence of peroxides, like benzoyl peroxide, C6H5CO2O2, or even just lighter trace oxygen, which can generate peroxide radicals. Under these specific conditions, the addition of HBr takes place contrary to Markovnikov's rule. The negative part, Br, adds to the carbon atom of the double bond that has the more hydrogen atoms. So if we add HBr to propene, CH3CH2, in the presence of peroxide, the major product formed is 1-bromopropane, CH3CH2CH2Br. Notice it's the opposite outcome compared to the reaction without peroxide. Why the difference? This reaction proceeds via a completely different mechanism, a free radical chain mechanism, not an ionic carbocation mechanism. Let's look at the key steps. Initiation. The peroxide first breaks down homolytically to form radicals. These radicals then react with HBr to generate a bromine radical, Br. Propagation. The bromine radical, Br, is the species that attacks the alkene's double bond. Now here's the crucial part regarding regiochemistry. The manure radical adds to the double bond in such a way as to form the more stable free radical intermediate. For propene, if Br adds to the terminal carbon, CH2, it forms a more stable secondary alkyl radical, CH3CH2Br.
If it added to the middle carbon, CH, it would form a less stable primary radical. CH3 is incorrect. It forms CH3CBr, which is secondary. Let me rephrase. If the rod adds to the middle carbon, it forms CH3CHBr, or a primary radical. The secondary radical, CH3CH2Br, is formed preferentially. The secondary radical then abstracts a hydrogen atom from another molecule of HBr, forming the product 1-bromopropane and regenerating a Br radical to continue the chain. So the anti-Markovnikov outcome is due to the formation of the more stable free radical intermediate in the propagation step. A common question is, why does this peroxide effect only work for HBr? Well, for HCl, the HEA bond is too strong to be broken homolytically by the radicals formed from the peroxide initiator. For HI, the HA bond is quite weak and it breaks easily, but the resulting iodine radicals are not very reactive. They tend to just combine with each other, I plus IOA2, rather than adding effectively to the alkene double bond. So HBr is just the right bond strength to work efficiently in this free radical chain mechanism. Let's apply this.
Problem 9.12 asks for the products of HBr addition to hex 1A. 1. Without peroxide, it follows Markovnikov's rule. Br adds to C2, fewer H's, giving 2-bromohexane. With peroxide, it follows the anti-Markovnikov pathway. Br adds to C1, more H's, giving 1-bromohexane. You must be able to predict both outcomes based on the presence or absence of peroxide. Practice this distinction thoroughly. 4. Addition of sulfuric acid. Cold, concentrated H2SO4 also adds across the double bond according to Markovnikov's rule, forming alkyl hydrogen sulfates. 5. Addition of water, hydration. Alkenes reacts with water, usually in the presence of a few drops of concentrated H2SO4 as a catalyst, to form alcohols. This addition also follows Markovnikov's rule. For example, propene hydrates to form propan-2-ene. 6. Oxidation. Alkenes are readily oxidized, using Bayer's reagent, which is cold, dilute aqueous potassium permanganate, KMNO4 solution, which is purple. When reacted with an alkene, the KMNO4 is reduced to manganese dioxide, MnO2, a brown precipitate, and the alkene is oxidized to form a vicinal diol, a glycol with unco-H groups on adjacent carbons. The disappearance of the purple color of KMNO4 is another test for unsaturation. For example, ethene gives ethane 1,2-diol. Stronger oxidation, using acidic or hot alkaline KMNO4, or acidic potassium dichromate, K2Cr2O7, can actually cleave the double bond entirely, oxidizing the fragments to ketones and or carboxylic acids, depending on the structure of the alkene. 7. Ozonolysis. This is a very important reaction, especially for structure determination. Alkenes react with ozone, O3, to initially form an unstable cyclic intermediate called an ozonide. This ozonide is then cleaved productively, typically by treatment with zinc dust and water, CnH2O. This cleavage breaks the original double bond, and each of the original double-bonded carbons becomes a carbonyl group, CNO. Depending on the substitution pattern of the original alkene, this results in the formation of aldehydes and ketones. The power of ozonolysis lies in its application. By identifying the aldehydes and ketones produced after cleavage, you can work backward to deduce the exact structure and position of the double bond in the original unknown alkene. This is a very common and important application-based question type in competitive exams. Practice working forwards, predicting products, and backwards, deducing structure from products. 8. Polymerization. This is a reaction of immense industrial importance. Under specific conditions, high temperature, high pressure, and often a catalyst, many small alkene molecules called monomers can add to each other repeatedly to form very large molecules called polymers. For example, ethene monomers polymerize to form polyethylene, polyethylene, and propene monomers form polypropylene. These polymers form the basis of the vast majority of plastics used today in packaging, bags, bottles, textiles, containers, toys, etc. While these materials have revolutionized modern life, their persistence and non-biodegradability raise significant environmental concerns regarding plastic waste.
The addition reactions are clearly the hallmark of alkenes, with Markovnikov and anti-Markovnikov rules being absolutely critical for competitive success. The application of ozonolysis in structure determination is also a key point. Now, let's turn our attention to the compounds with triple bonds. Alkenes.
Yes, alkanes. These are unsaturated hydrocarbons characterized by the presence of at least one carbon-carbon triple bond. Having a triple bond means they have even fewer hydrogen atoms than the corresponding alkenes or alkenes. Their general formula is CnH2 and 2. The first stable member of the alkane series is ethene, C2H2, which is much more commonly known by its trivial name, acetylene. Acetylene is industrially very important. It burns with a very hot flame when mixed with oxygen, the oxyacetylene flame, which is used for welding and cutting metals. It's also a crucial starting material for synthesizing many other organic chemicals. For IUPAC nomenclature, the rules are similar to alkenes, but the suffixes change from -ane to -ane. Again, you select the longest chain containing the triple bond and number it to give the triple bond the lowest possible number. Ethene, C2H2, and propyne, C3H4, have only one possible structure each, but starting with butane, C4H6, position isomerism becomes possible. There are two isomers, but one dene, triple bond starts at C1, and butane, triple bond starts at C2. Problem 9.13 in your textbook asks for the isomers of C6H10, which is the fifth member of the alkane series, starting from ethene C2. There are actually 7 such structural isomers. Finding them requires a systematic approach. Start with straight chain structures varying the triple bond position, hex 1-tine, hex 2-tine, hex 3 isomers. Then consider a 5-carbon main chain, pentyne, with a methyl branch. Place the branch in the triple bond in all unique combinations. 3-methylpen 1-tine, 4-methylpen 1-tine, 4-methylpen 2-tine, another 3 isomers. Then consider a 5-carbon main chain, pentyne, with a methyl branch. Place the branch and the triple bond in all unique combinations. Finally, consider a highly branched 4-carbon main chain, pentyne, with 2 methyl branches. The only possibility here is 3.3 diol one di, 1 isomer. So in total, 3 plus 3 plus 1 equals 7 approaches. Identifying them involves carefully applying the rules for chain and position isomerism, just like we did for alkenes and alkanes.
Understanding the isomerism is important, but first, understanding the triple bond structure itself is key. How is it formed, and how does it influence their properties, especially that unique linear geometry we see in alkynes?
Excellent question. Let's visualize the triple bond, using ethene, acetylene, as our primary example. The key feature is that each carbon atom involved in the triple bond is spa hybridized. Remember, spot hybridization leads to linear geometry. So how are the bonds formed in ethene, HCCH? Each spa hybridization forms 2 sigma bonds. One CA sigma is formed by the head-on overlap of one spa hybrid orbital from each carbon. One CH sigma is formed by the overlap of the other spa hybrid orbital on carbon with the 1th orbital of hydrogen. Since orbitals are oriented 180 degrees apart, this arrangement forces the HCC and CCH bond angles to be exactly 180 degrees, making the entire ethene molecule perfectly linear. Now, what about the triple bond itself? After forming the sigma bonds, each sp hybridized carbon still has 2 unhybridized p orbitals remaining, say pi and pz. These p orbitals are perpendicular to each other and also perpendicular to the axis of the pi hybrid orbitals, the sigma bond axis. These p orbitals on adjacent carbons overlap laterally or sideways. The pi orbital on one carbon overlaps with the pi orbital on the other, forming one pi bond. Similarly, the pz orbital on one carbon overlaps with the ps on the other, forming a second pi bond. So a carbon triple bond consists of one strong sigma bond and 2 weaker pi bonds. The electron density of these 2 pi bonds forms a sort of cylinder surrounding the CC sigma bond axis. Let's compare bond strength and length again. The CC triple bond is the strongest of the carbon bonds, around 823 kilogemoles, and also the shortest, about 120 pm. This compares to CC 134 pm, 681 kilomole, and CC 154 pm, 340 kilomole. These differences in bond energy and length are crucial for understanding their relative reactivities.
The linear structure and the presence of 2 pi bonds are certainly distinctive features. How are these alkynes typically prepared?
There are 2 main methods that are prominent for preparing alkynes, especially ethanol. 1. From calcium carbide. This is the primary industrial method for producing large quantities of ethane, acetylene. It's a 2-step process. First, quicklime, calcium oxide, CaO, which is obtained by heating limestone, calcium carbonate, KCO3, is heated with coke, carbon, at very high temperatures, around 273 K, in an electric furnace. This produces calcium carbide, CaK2, and carbon monoxide. Second, calcium carbide is then reacted simply with water at room temperature. This reaction generates ethane gas and calcium hydroxide, slaked lime. Ca2 plus 2H2O is C2H2 plus KOH2. This is a very efficient large-scale method. 2. from vicinal to halides. This is a common laboratory method and involves a double dehydroethanogenation, removal of 2 molecules of HX. It's usually a 2-step elimination process because the second elimination is harder than the first. First, the vicinal dihalide, like 1-dibromethane, is treated with alcoholic KOH. This removes 1 molecule of HX, HBr in this case, via elimination, forming an alkynyl halide, like vinyl bromide, CH2CHBr.
Second, this alkynyl halide is less reactive towards elimination than the original alkyl halide. So to remove the second molecule of HX, a much stronger base is required, typically sodamide, NH2, dissolved in liquid ammonia. Sodamide removes the second HX, forming the alkyne triple bond. For example, 1-Gol2-dibromethane can be converted to ethane using alcoholic KOH, followed by NaNH2. Similarly, 1-Gol2-dibromopropane would yield propane.
The preparation from calcium carbide is a classic industrial route. Now let's move to their properties, particularly their unique acidic character, which, as you mentioned earlier, is a key distinguishing feature, especially important for competitive exams.
Yes, the acidic nature of certain alkanes is a very important concept. Let's cover physical properties briefly first. They follow similar trends to alkanes and alkenes. The first few members, ethene, propyne, butane, are gases at room temperature. The next 8 are liquids, and higher ones are solids. All are colorless. Ethene has a characteristic somewhat garlic-like odor when impure, but pure alkynes are generally odorless. They are weakly polar, insoluble, or only very slightly soluble in water, but readily soluble in organic solvents like benzene or ether. Their melting points, boiling points, and densities generally increase with increasing molar mass. Now let's focus on their chemical properties, starting with the most unique one. A. Acidic character of alkanes. Critical for exams. This acidity is specific to terminal alkynes that have the triple bond at the end of the carbon chain, meaning they have a hydrogen atom directly attached to a triply bonded carbon, like HTCH or RCCH. Alkynes with the triple bond in the middle of the chain, internal alkynes or ES, where R and R are alkyl groups, do not show this acidic character. Okay, why are terminal alkanes acidic? This is the why it matters part for conceptual understanding. It all comes down to the hybridization of the carbon atom holding the hydrogen. In the terminal alkyne, the hydrogen is attached to an Ansbach hybridized carbon atom. Remember, an Ansbach hybrid orbital has 50% character compared to 33% for sp2 and alkenes and 25% for sp3 and alkenes. The s orbital is closer to the nucleus than p orbitals. Therefore, the more F's character an orbital has, the closer its electrons are held to the nucleus and the more electronegative that carbon atom becomes. This high electronegativity of the sp carbon in a terminal alkyne strongly attracts the shared electron pair, the CH bond, towards itself. This weakens the CH bond and makes it easier for the hydrogen atom to be released as a proton, H+, especially when reacted with a strong base. This acidity, while weak compared to water or alcohols, is significantly greater than that of alkenes or alkenes. The acidity order is HCSEH2CH3H3CH3. Also, SA is more acidic than propion, which is much more acidic than an internal alkene like bituonine, which is essentially non-acidic at the CH bonds not attached to the triple bond. How is this acidity demonstrated? Terminal alkynes react with very strong bases like sodium metal or, more commonly, sodamide NNH2 in liquid ammonia. In these reactions, the acidic hydrogen is removed, and an ionic compound called an acetylide or alkanide is formed, along with the liberation of dihydrogen gas with Na, or ammonia gas with NaNH2. Example, H3CH plus NaNH2 plus sodium methanide plus 12H2. Example, CH3CCH plus NaNH2 CH3C Na plus sodium propanide plus NH3. These reactions are extremely useful because they provide a simple chemical test to distinguish terminal alkynes from internal alkynes, alkenes, and alkenes. Only terminal alkynes will react with Na or NaNH2 to produce a salt, acetylide, and evolve gas. This is a very common application tested in labs and exams. B. Addition reactions. Like Alkenes alkynes undergo addition reactions because of their pi bonds. Since they have 2 pi bonds, they can typically add 2 molecules of the reagent across the triple bond. The addition usually proceeds in steps, first forming an alkene derivative, which can then react further to form a saturated derivative. For additions to unsymmetrical alkynes, the first addition generally follows Markovnikov's rule. Let's look at the main addition reactions. 1. Addition of dihydrogen, hydrogenation. Catalytic hydrogenation, using PT, PD, or Ni, converts alkenes first to alkenes, and then if enough hydrogen is supplied further to alkenes, for example, ethene, ethene, ethene. Remember, using Lindlar's catalyst allows stopping at the cis-alkene stage. Addition of halogens, halogenation. Alkenes react with halogens like Br2 or Cl2. They readily decolorize bromine water, another test for unsaturation. Addition occurs stepwise. First, one molecule adds to form a dihaloalkane, and then a second molecule adds to form a tetrahaloalkane. For example, ethene plus Br2 hydrogenation. Alkenes add 2 molecules of HX, HCl, HBr, HAI. The first addition follows Markovnikov's rule if the alkene is unsymmetrical. The second addition also typically follows Markovnikov's rule, leading to the formation of a geminal dihalide, or gemdihalide, meaning both halogen atoms end up attached to the same carbon atom. For example, ethene plus HBr, bromothene plus HBr, 1,1 would 1 T-bromethy. 4. Addition of water, hydration. This is a very important reaction. Alkanes add water, but the reaction requires specific catalysts. Typically, mercuric sulfate, HCSO4, dissolved in dilute sulfuric acid, H2SO4, usually carried out around 333 K, 60 degrees C. The initial addition follows Markovnikov's rule and forms an unstable intermediate called an enol, a compound with an iso-H group attached to a double-bonded carbon. Enols rapidly rearrange, tautomerize into more stable carbonyl compounds, aldehydes or ketones. 4. Addition of water, hydration. Ethene, acetylene, is the only alkene that yields an aldehyde, ethynyl acetaldehyde, upon hydration. 4. Addition of water, hydration. All other terminal alkynes, RCACH, yield methyl ketones, RCOCH3, upon hydration, following Markovnikov addition of H+ and OH. For example, propyne hydrates to give propanol, acetone. C. Polymerization. Alkanes can also undergo polymerization. A. Linear polymerization. Under suitable conditions, ethene can polymerize linearly to form polyacetylene or polyethylene. This is a long-chain polymer with repeating CH units. Polyacetylene is interesting because when doped, it can conduct electricity, making it a conducting polymer with potential applications in batteries and electronics. A. Linear polymerization. B. Cyclic polymerization. This is a crucially important reaction for exams, especially for synthesis questions connecting aliphatic and aromatic chemistry. When ethane, acetylene gas, is passed through a red-hot iron tubes or quartz tube maintained at a high temperature, around 873 K or 600 degrees C, 3 molecules of ethane undergo cyclic polymerization to form 1 molecule of benzene, C6H6. Significance. This is a classic and direct method to convert a simple aliphatic compound, ethane, into a fundamental aromatic compound, benzene. Remember this transformation. Problem 9.14 asks, how will you convert ethanoic acid into benzene? This requires linking reactions we've learned. Okay, let's outline the path. Problem 9.14 asks, 1. Start with ethanoic acid, CH3COH. React it with NaBOH to get its sodium salt, sodium ethanoate, CH3COEO. Problem 9.14 asks, 2. Perform decarboxylation of sodium ethanoate using soda lime, NaOH plus CaO. Heat. That removes CO2 and gives methane CH4. Remember, decarboxylation gives 1 carbon less.
Problem 9.14 asks, 3. Now we need ethene from methane. This is usually done industrially by partial oxidation of methane at very high temperatures, around 1500 degrees C, or via conversion to chloromethane, then Wirth's reaction to ethane, then chlorination to dichloroethane, then double dehydrogenation. Let's assume we can get ethene, C2H2, from methane precursors. Problem 9.14 asks, 4. Finally, take the ethane C2H2 and pass it through a red-hot iron tube at 873 K. This cyclic polymerization yields benzene, C6H6. Problem 9.14 asks, this type of multi-step synthesis problem requiring you to connect different reactions is very common in competitive exams.
The acidic nature of terminal alkynes, and especially their direct conversion to benzene via cyclic polymerization, are highly significant takeaways for our listeners. That brings us very neatly to our final major category. Aromatic hydrocarbons, with the star of the show, the intriguing molecule benzene.
Indeed. Let's now explore the fascinating world of aromatic hydrocarbons, also commonly called arenes. Historically, the term aromatic arose because many of the early examples discovered, like from plant extracts, had pleasant fragrances or aromas. However, the chemical definition today is based on structure and stability, not smell. Their defining characteristic is the presence of a special type of cyclic unsaturation, most often involving 1 or more benzene rings. We broadly classify them into benzenoids. These are aromatic compounds that contain at least 1 benzene ring in their structure. Examples include benzene itself, toluene, methylbenzene, naphthalene, 2 fused benzene rings found in mothballs, anthracene, 3 fused rings, biphenyl, 2 benzene rings linked by a single bond. Most of the aromatic compounds you'll study fall into this category. Non-benzenoids. These are compounds that exhibit aromatic character, meeting criteria like Hückel's rule, but do not contain a benzene ring. Examples include azolene or some charged cyclic species like the cyclopentadienyl anion. We'll focus mainly on benzenoids here. For nomenclature, we need to recall the basics, often covered in earlier units, but crucial here. In benzene, C6H6, all 6 carbon atoms and all 6 hydrogen atoms are chemically equivalent due to symmetry. Therefore, there is only 1 possible monosubstituted benzene derivative. For example, only 1 chlorobenzene, only 1 methylbenzene and toluene. For dis-substituted benzenes, however, 3 positional isomers are possible. We use prefixes to distinguish them. Ortho. Substituents are on adjacent carbons, positions 1 and 2. Meta-M, substituents are separated by one carbon, positions 1 and 3. Para, substituents are on opposite carbons across the ring, positions 1 to 4. For example, dimethylbenzene exists as O-xylene, 1,4-dimethylbenzene, M-xylene, 1,3-dimethylbenzene, and P-xylene, 1,4-dimethylbenzene. Mastering this naming system is fundamental.
The benzene ring is truly iconic in organic chemistry. Its structure puzzled chemists for such a long time because despite its formula, C6H6, suggesting a high degree of unsaturation like alkynes, it's unusually stable and surprisingly resistant to the addition reactions typical of alkenes and alkynes. Instead, it prefers substitution reactions. Could you explain the mystery behind its structure and what exactly makes it aromatic?
Absolutely. Benzene, C6H6, first isolated by Michael Faraday in 1825, presented a major structural puzzle. Its molecular formula indicated high unsaturation, yet its chemical behavior was very different from typical unsaturated compounds. It was remarkably stable and favored substitution over addition. Let's unpack this journey. The first significant proposal came from August Hückel in 1865. He suggested a cyclic structure of 6 carbon atoms arranged in a hexagon, with alternating single and double bonds and 1 hydrogen atom attached to each carbon. This structure accounted for the formula C6H6 and the fact that all hydrogens were equivalent. However, Hückel's original structure had problems. For instance, it predicted that there should be 2 different isomers of 1,2-dibromobenzene, one where the bromines are across a double bond, one where they are across a single bond. But experimentally, only 1 isomer of 1,5,2-dibromobenzene was ever found. To account for this, Hückel later modified his proposal, suggesting that the double bonds were not fixed, but rapidly oscillating or shifting positions within the ring.
While a brilliant insight for its time, even the oscillating Hückel structure couldn't fully explain benzene's unusual lack of reactivity towards addition reactions and its extraordinary thermodynamic stability compared to hypothetical cyclohexatrine with fixed double bonds. There's a famous anecdote associated with this discovery. Hückel apparently described his inspiration for the cyclic structure coming from a dream he had of a snake seizing its own tail, forming a ring. It's a nice story illustrating how sometimes breakthroughs can come from unexpected places, combining intuition with rigorous scientific thought. The true explanation for benzene's unique properties lies in the concepts of resonance and electron delocalization. This is absolutely critical for your understanding. Benzene is best described as a resonance hybrid of several contributing structures. The 2 Hückel structures, with alternating double bonds in different positions, are the major contributors. The actual structure is an average or hybrid of these forms. The most accurate picture comes from considering the orbital overlap. Let's visualize this, referencing Fig 9.7 in your text. All 6 carbon atoms in the benzene ring are sp2 hybridized. This means they form a planar hexagonal sigma bond framework. Each carbon forms sigma bonds to 2 adjacent carbons, using sp2-sp2 overlap, and 1 hydrogen, using sp2-1's overlap. All bond angles are 120 degrees, resulting in a flat hexagonal ring. Now, each sp2 hybridized carbon atom also has 1 unhybridized p orbital remaining, which is oriented perpendicular to the plane of the ring, 1 lobe above the plane, 1 lobe below. Here's the crucial point. These 6 parallel p orbitals, 1 on each carbon, are close enough to overlap laterally with their neighbors on both sides. This continuous sideways overlap extends all the way around the ring. Here's the crucial point. Instead of forming 3 localized pi bonds, as in the Hückel structures, the 6 pi electrons, 1 from each p orbital, become delocalized over the entire ring. They form a continuous pi electron cloud, 1 donut-shaped cloud above the plane of the ring, and another identical cloud below the plane. This delocalization is the key to benzene's stability. The 6 pi electrons are not confined between specific pairs of carbon atoms. They are shared equally by all 6 carbons in the ring. This extensive delocalization lowers the overall energy of the molecule significantly compared to a structure with localized double bonds. This extra stability due to delocalization is often called resonance energy. There's strong experimental evidence supporting this delocalized picture. X-ray diffraction studies show that benzene is perfectly planar. Crucially, all 6 carbon bond lengths in benzene are identical, measured at 139 picometers PM. This value is intermediate between the typical length of a CC single bond, around 154 PM, and a CT double bond, around 133 PM. If benzene had fixed alternating single and double bonds, we would expect 2 different bond lengths, but we observe only 1. This uniformity strongly supports the idea of delocalized pi electrons shared equally around the ring. This delocalized structure also explains benzene's chemical behavior. It resists addition reactions because addition would require breaking the stable, delocalized aromatic pi system. Instead, it undergoes substitution reactions where a hydrogen atom is replaced, because this allows the stable aromatic system to remain intact. Now, this leads us to the formal definition of aromaticity and Hückel's rule. This is a highly testable area.
For any cyclic planar system to be considered aromatic, it must satisfy these conditions. Body planarity. The molecule or the relevant part of the molecule must be planar, or nearly planar, to allow effective overlap of the p orbitals. 2. Complete delocalization. There must be a continuous cycle of overlapping p orbitals, allowing the pi electrons to be completely delocalized around the ring. There should be no sp3 hybridized atoms within the ring interrupting the cycle. 3. Hückel's rule. The cyclic system must possess a specific number of pi electrons, given by the formula 4n plus 2 electrons, where n is a non-negative integer, n is 0, 1, 2, 3. Let's apply Hückel's rule. For benzene, its planar has complete delocalization and has 6 pi electrons. Does 6 fit 4n plus 2? Yes, if n equals 1, 41 plus 2 equals 6. So benzene is aromatic. For naphthalene, C10H8, it's planar delocalized and has 10 pi electrons. Does 10 fit 4n plus 2? Yes, if n is 2, 42 plus 2 equals 10. So naphthalene is aromatic. Consider cyclobutadiene, C4H4. Its cyclic can be planar but has 4 pi electrons. Does 4 fit 4n plus 2? No, there's no integer n that satisfies this.
Cyclobutadiene follows the 4n rule, n1, and is actually anti-aromatic and very unstable. So Hückel's rule, 4n plus 2 pi electrons, is a fundamental criterion for identifying aromatic compounds in your exams. Remember these 3 conditions: planar, fully conjugated cyclic system, and 4n plus 2 pi electrons.
The concept of resonance leading to delocalization and the quantitative Hückel's rule for predicting aromaticity are absolutely fundamental for understanding these compounds. Your explanation makes the stability and reactivity very clear. Now, how is benzene typically prepared apart from the coal tar source?
Right, commercially, benzene is indeed primarily isolated from coal tar through fractional distillation and also produced during petroleum refining processes like catalytic reforming. For laboratory synthesis, we have a few key methods we should know. 1. Cyclic polymerization of ethene. We discussed this under alkyne reactions, but it's worth reiterating here as a primary synthesis route to benzene. Passing 3 molecules of ethene, acetylene, through a red-hot iron tube at 873 K causes them to cyclize and form 1 molecule of benzene. Remember this direct aliphatic to aromatic conversion. 2. Decarboxylation of aromatic acids. Similar to the decarboxylation of aliphatic carboxylic acid salts we saw earlier. If you take the sodium salt of benzoic acid, sodium benzoate, C6H5COONA, and heat it strongly with soda lime, NeOH plus COO, the carboxylate group, keona, is removed to sodium carbonate, and you are left with benzene, C6H6. C6H5CON plus NaOH, CaO, heat, C6H6 plus NaOCO3. 3. Reduction of phenol. Phenol, C6H5OH, is benzene with an NOH group attached. If you pass phenol vapors over heated zinc dust, the zinc acts as a reducing agent, removing the oxygen atom as ZNO and leaving behind benzene, C6H6. C6H5OH plus ZN, C6H6 plus ZNO. This is a simple and effective laboratory method.
That's a good summary of its preparation routes. Now, let's explore the signature reactions of benzene and other aromatic hydrocarbons. What makes them react the way they do, favoring substitution, as you explained?
It's exactly. Aromatic hydrocarbons like benzene have characteristic properties. Physically, they're generally nonpolar, often colorless liquids or solids like naphthalene, with a characteristic aroma, though not always pleasant, and many are toxic. They are immiscible with water, but miscible with common organic solvents. A key observation when they burn is that they typically produce a sooty flame. This is due to their high carbon-to-hydrogen ratio compared to alkanes, leading to incomplete combustion and the formation of carbon particles. Soot. Their chemical properties, however, are dominated by electrophilic substitution reactions, often abbreviated as CER electrophilic aromatic substitution. As we discussed, the high stability of the aromatic ring makes it resistant to addition reactions, which would destroy the aromaticity. And instead, an electrophile, E+, an electron-seeking species, attacks the electron-rich pi cloud of the benzene ring and replaces one of the hydrogen atoms on the ring, leaving the stable aromatic system intact. Let's quickly overview the main types of electrophilic substitution reactions you absolutely need to know for your exams. I. Nitration. This involves the introduction of a nitro group, NO2, onto the ring. Conditions. Achieved by heating benzene with a nitrating mixture, which is a mixture of concentrated nitric acid, conc HNO3, and concentrated sulfuric acid, conc H2SO4. Product. Nitrobenzene, C6H5NO2, halogenation. Introduction of a halogen atom, NSX, usually Cl or Br, onto the ring. Conditions. Requires reaction of benzene with a halogen Cl2 or Br2 in the presence of a Lewis acid catalyst, such as anhydrous iron, chloride, FeCl3, iron 3 bromide, Eb3, or aluminum chloride, AlCl3. The Lewis acid helps generate the electrophilic halogen species. Direct reaction with halogens without a catalyst is very slow. Product. Haloarenes, for example, chlorobenzene, C6H5Cl, or bromobenzene, C6H5Br. Sulfonation, replacement of a hydrogen atom by a sulfonic acid group, SO3H. Conditions, achieved by heating benzene with fuming sulfuric acid. Oleum, which is concentrated H2SO4 containing dissolved sulfur trioxide, SO3. SO3 acts as the electrophile here. This reaction is often reversible. Product, benzene sulfonic acid, C6H5SO3H, 4-Friedel-Crafts alkylation. Introduction of an alkyl group R onto the ring.
Named after Charles Friedel and James Crafts. Conditions, reaction of benzene with an alkylalide, RX, in the presence of a Lewis acid catalyst, typically anhydrous aluminum chloride, AlCl3. Product, alkyl benzene, e.g., reacting benzene with methyl chloride, CH3Cl, gives methylbenzene, which is toluene, C6H5CH3, important caveat carbocation rearrangement. Be very careful with Friedel-Crafts alkylation using primary alkylalides longer than ethyl. A common exam question involves reacting benzene with 1-chloropropane, CH3CH2CH2Cl, and AlCl3. You might expect the product to be propylbenzene. However, the major product formed is actually isopropylbenzene, Q-many. Why? The Lewis acid helps form the primary carbocation, CH3CH2CH2+. This primary carbocation is unstable and rapidly rearranges via hydride shift. A hydrogen atom with its electron pair moves from the middle carbon to the end carbon to form the much more stable secondary carbocation, CH3CH plus CH3, the isopropyl carbocation. It is this more stable secondary carbocation that then attacks the benzene ring as the electrophile, leading to isopropyl benzene.
This rearrangement is a crucial concept to remember for predicting products in Friedel-Crafts alkylation. V. Friedel-Crafts acylation. Introduction of an acyl group, -COR, where R is an alkyl or aryl group, onto the ring. Conditions, reaction of benzene with an acyl halide, RCOCl, or an acid anhydride, RCO2O, in the presence of a Lewis acid catalyst, like anhydrous AlCl3. Product, an acyl benzene, which is an aromatic ketone, again, the reacting benzene with acetyl chloride, CH3COCl, gives acetophenone, C6H5COCO3. Advantage over alkylation. Importantly, the acyl group, RCO+, is resonance stabilized and does not undergo rearrangement like alkyl carbocations do. Also, the product ketone is deactivated towards further substitution. We'll see why later, preventing multiple acylations, which can be a problem in alkylation. It's also possible to have further substitution if you use excess electrophile or more forcing conditions. For example, reacting benzene with excess chlorine in the presence of AlCO3 can eventually lead to hexachlorobenzene, P6CO6. Okay, now let's understand the mechanism of electrophilic aromatic substitution, ARED. This is extremely important for competitive exams, as mechanism-based questions are very common. It's generally a 3-step process, common to all the reactions we just discussed. Step A, generation of the electrophile, E+. The first step is always the formation of a strong electrophile. How it's formed depends on the specific reaction. For halogenation, the Lewis acid, example FeCl3, reacts with the halogen Cl2 to generate the electrophilic species like Cl+, or a complex that delivers Cl+, FeCl3 plus Cl2, FeCl4 plus Cl plus air. For Friedel-Crafts alkylation, the Lewis acid, LCl3, reacts with the alkyl halide, RFC, to generate the carbocation electrophile, R+. RCl plus LCl3, ARSCO plus LCl4. Remember potential rearrangement here for Friedel-Crafts acylation. The Lewis acid, LCl3, reacts with the acyl halide, RCl plus LCl plus, RCl plus LCl3, RCl plus LCl4. For nitration, here sulfuric acid acts as a stronger acid, protonating nitric acid. The protonated nitric acid then loses water to form the powerful nitronium ion electrophile 10 plus HNO3 plus 2H2SO4, NO2 plus H3O plus 2HSO4. Sulfuric acid's role here is crucial to generate the actual electrophile, NO2 plus SO, for sulfonation. The electrophile is usually sulfur trioxide, SO3, present in oleum or generated from H2SO4 itself. Step B, formation of the carbocation intermediate, a rhenium ion or complex. The generated electrophile, E+, is electron deficient and attacks the electron-rich pi cloud of the benzene ring. This forms a Ce bond. In this process, the carbon atom that forms the bond becomes D3 hybridized, and the air momenticity of the ring is temporarily broken. The positive charge is delocalized over the remaining 5 sp2 carbons of the ring via resonance. This resonance-stabilized carbocation intermediate is called an rhenium ion or a sigma complex. You should be able to draw the resonance structure showing the delocalization of this positive charge, usually at the ortho and para positions relative to where the electrophile attacked. This step is usually the slow, rate-determining step of the reaction. Step C, removal of proton. To restore the very stable aromatic system, the rhenium ion intermediate must lose a proton, H+, from the same carbon atom that the electrophile attacked, this E3 hybridized carbon. This proton is removed by a base present in the reaction mixture, typically the counterion generated in step A, like AlCl4 or HSO4. The electrons from the CH bond collapse back into the ring, reforming the pi system and restoring aromaticity. The final product is the substituted benzene, and the catalyst, like LCl3 or H2SO4, is regenerated. Understanding these three fundamental steps, electrophile generation, iridium ion formation, rate determining, and proton removal, restoring aromaticity, is absolutely key to mastering electrophilic aromatic substitution. While substitution is characteristic, benzene can also undergo addition reactions, but only under much more vigorous conditions that can overcome the aromatic stability. Hydrogenation. If you react benzene with excess hydrogen gas, 3H2, at high temperature and pressure, using catalysts like nickel, platinum, or palladium, the aromatic ring can be completely saturated to form cyclohexane, C6H11. All double bonds are reduced. Halogenation under UV light. This is different from electrophilic halogenation. If you react benzene with excess chlorine, 3Cl2, and the presence of ultraviolet UV light, in absence of Lewis acid catalysts, addition occurs via a free radical mechanism. Each double bond adds a Cl2 molecule, resulting in benzene hexachloride, BHC, C6H6Cl6. One specific isomer of BHC, called gamma BHC or gamoxane or lindane, is a powerful insecticide, though its use is now restricted due to environmental concerns. Finally, like all hydrocarbons, benzene undergoes combustion when burned in oxygen, producing carbon dioxide and water, typically with a very sooty flame due to its high carbon content. The general equation is CXY plus X plus Y4V2 at CO2 plus Y2H2O.
The electrophilic substitution mechanism is truly a cornerstone of organic chemistry, and your detailed step-by-step breakdown is very helpful for exam preparation. Finally, let's look at a very practical aspect. How do substituents already present on a benzene ring influence where the next substituent goes? This directive influence is crucial for planning syntheses, right?
Absolutely. This concept, the directive influence of a functional group in monosubstituted benzene, is crucial for predicting the products of further substitution reactions, a very common scenario in multi-step synthesis problems in competitive exams. When a monosubstituted benzene, like toluene or nitrobenzene, undergoes a second electrophilic substitution reaction, the incoming electrophile, E+, doesn't attach randomly to any of the remaining 5 positions. The position it takes, ortho, meta, or para relative to the first substituent, is strongly influenced or directed by the nature of the substituent already present on the ring. It's the group already there that calls the shots, not the incoming group. We can broadly classify existing substituents into 2 main categories based on their directive influence. 1. Ortho and para directing groups. These groups direct the incoming electrophile primarily to the ortho and para 1 or 4 positions relative to themselves. Usually a mixture of ortho and para isomers is formed, with the ratio often depending on steric factors. The ortho positions might be sterically hindered if the existing group or the incoming group is large. Okay, why do they direct ortho-para? Let's think about the mechanism using the SOH group in phenol as an example. The oxygen atom in the SOH group has lone pairs of electrons. It can donate one of these lone pairs into the benzene ring via resonance. This is called the plus M or plus R effect. When you draw the resonance structures for phenol, you'll see that this electron donation places negative charges, or increased electron density, specifically at the ortho and para positions of the ring. The meta positions remain relatively unaffected. Since the incoming electrophile E+ is seeking electrons, it will preferentially attack these more electron-rich ortho and para sites. Most ortho-para directing groups are also activating groups. This means they not only direct ortho-para, but also make the benzene ring more reactive toward electrophilic substitution compared to benzene itself. This is because their electron-donating nature, either through resonance like OVH-NH2, DANH-OCH3, DANH-NH3OCH3, or through inductive effect like alkyl groups ANH-CH3, DANH-C2H5, increases the overall electron density of the ring, making it more attractive to electrophiles. Halogens, F, FCl, Br, DANH-I, are the important exception. They are ortho-para directing, but are simultaneously deactivating groups. This is a highly testable point. Why ortho-para directing? Like OH, halogens also have lone pairs that can be donated into the ring via resonance, plus M effect, increasing electron density preferentially at the ortho and para positions. If you draw resonance structures for chlorobenzene, you'll see negative charges appearing at the O and P carbons. This makes these positions the preferred sites for electrophilic attack compared to the meta position. Why deactivating? However, halogens are also highly electronegative. They exert a strong electron-withdrawing inductive effect through the sigma bond, pulling electron density away from the entire ring. For halogens, this electron-withdrawing inductive effect is stronger than their electron-donating resonance effect, plus M. The net result is that the overall electron density on the chlorobenzene ring is less than that on benzene itself, making it less reactive deactivated toward electrophiles. But among the positions available, the O and P positions are still relatively less deactivated or more activated than the MEN position due to the resonance effect. So attack still occurs primarily at orthopara, just slower than in benzene. Understand this balance between inductive and resonance effects for halogens is crucial. 2. Meta-directing groups. These groups direct the incoming electrophile primarily to the meta 1/3 position relative to themselves. Why meta? Let's consider the NO2 group in nitrobenzene as an example. The nitro group is a strong electron withdrawing group, both through resonance, MR effect, it pulls electrons out of the ring, and induction, di effect. When you draw the resonance structures for nitrobenzene, you'll find that positive charges appear on the carbon atoms at the ortho and para positions. This means the ortho and para positions become significantly electron deficient. The meta positions, while still somewhat deactivated by the inductive effect, do not bear this formal positive charge in the resonance structures. Therefore, the incoming electrophile, E+, which is seeking electrons, finds the meta position to be the least electron deficient or relatively most electron-rich site available in the ring and attacks there. All meta-directing groups are also deactivating groups. They strongly decrease the overall electron density of the benzene ring, making it much less reactive toward electrophilic substitution than benzene itself. Examples include groups like etyldecyl cyano, CHO aldehyde, CO ketone, COH carboxylic acid, CO or ester, SO3H sulfonic acid. All these groups have a multiple bond connected to an electronegative atom directly attached to the ring, or a positive charge on the atom attached to the ring, facilitating electron withdrawal.
Understanding this directive influence, activating versus deactivating, and orthopara versus meta-directing is absolutely crucial for predicting reaction products in synthesis, a very common exam scenario. Your detailed explanation of the electronic effects, resonance, and inductive behind these influences is extremely helpful. Lastly, before we conclude, let's briefly touch upon the very real-world health aspects associated with some of these hydrocarbons.
Yes, that's a very important point to cover, even if briefly. While hydrocarbons are undeniably essential to our modern lives, powering our industries and providing materials, it's equally important to be aware that some of them pose significant health risks. Specifically, benzene itself is classified as a known human carcinogen, cancer-causing agent. Prolonged exposure to benzene vapors can lead to leukemia and other blood disorders. Additionally, a class of compounds called polynuclear aromatic hydrocarbons, PAHs, are of particular concern. These are complex molecules containing multiple, more than 2, benzene rings fused together in various arrangements. Many PAHs are also known to be potent carcinogens and mutagens, causing genetic mutations. How are these harmful compounds formed? They are typically generated as byproducts during the incomplete combustion of organic materials. Think about common sources like the smoke from burning tobacco. Cigarette smoke is a major source of PAHs. Emissions from coal combustion and power plants. Exhaust fumes from diesel and gasoline engines. Smoke from wood fires, and even grilled or charred food. When these materials don't burn completely due to insufficient oxygen or low temperatures, these complex, stable aromatic structures are formed. Once these compounds, like benzene or PAHs, for example, benzoprine, a well-studied example found in coal tar and tobacco smoke, enter the human body perhaps through inhalation of polluted air, ingestion of contaminated food, or skin contact, they can undergo metabolic activation. The body tries to process them, but sometimes these metabolic processes convert them into highly reactive intermediates, like epoxides. They can bind directly to our DNA, the genetic material within our cells. This binding can damage the DNA structure, leading to errors during DNA replication or repair. Accumulation of such DNA damage can disrupt normal cell function, interfere with cell cycle regulation, and ultimately lead to the uncontrolled cell growth and division that characterizes cancer. While you don't need to memorize the structures of all the PAHs listed in the textbook box, like 1-argithin-benzanthracene or 3-methylconanthrene, the key takeaway for you is the general understanding that benzene and polynuclear aromatic hydrocarbons, often formed from incomplete combustion, are toxic and carcinogenic, primarily because they, or their metabolites, can damage DNA. This highlights the importance of controlling emissions and minimizing exposure to such substances.
That's a sobering but very important note on the real-world implications and potential hazards of these compounds, reminding us that chemistry impacts our health and environment profoundly. Thank you for this incredibly detailed and structured deep dive into the world of hydrocarbons.
You're most welcome. It was a pleasure discussing it. To quickly summarize this extensive deep dive into hydrocarbons, we started with their fundamental definition as compounds of carbon and hydrogen and explored their classification into saturated alkanes, single bonds only, CnH2n+2, unsaturated amines, at least one C double bond, CnH2n, and alkenes, at least one CZ triple bond, CnH2n2, and the special class of aromatic compounds, exemplified by benzene. We delved into their unique structural features, the tetrahedral sp3 geometry of alkenes, leading to conformations, staggered eclipsed, the planar SME2 geometry around the double bond in alkenes, leading to geometrical cis-trans isomerism, the linear street geometry around the triple bond in alkanes, and the planar delocalized pi electron system conferring special stability, aromaticity, Hückel's rule, in benzene. We covered crucial methods of preparation, including hydrogenation, elimination reactions, dehydrohalogenation, dehydration, specific named reactions like Wirth's and Kolbe's for alkanes, partial reduction of alkanes, Lindlar's catalyst, and key benzene syntheses like cyclic polymerization of ethane and decarboxylation. We thoroughly discussed their diverse physical and chemical properties, focusing intently on characteristic reactions, free radical substitution, halogenation mechanism in alkanes, electrophilic additions in alkenes, including the vital Markovnikov and anti-Markovnikov peroxide effect rules and mechanisms, hydration, ozonolysis, the unique acidity of terminal alkynes, and the signature electrophilic substitution reactions, nitration, halogenation, sulfonation, Friedel-Crafts alkylation, acylation of aromatic compounds, breaking down the common CER mechanism. We also explored various types of isomerism relevant to each class, chain, position, functional, implied, conformational, and geometrical isomers, and critically analyzed how existing substituents direct further electrophilic substitution in benzene, activating, deactivating, or the para versus meta-directing effects. Finally, we briefly touched upon the important issue of carcinogenicity and toxicity associated with benzene and polynuclear aromatic hydrocarbons.
This has truly been an incredibly comprehensive and thoroughly structured session. It covered a vast amount of crucial information. For all you learners out there diligently preparing for your Class 11, 12, JG, or NEET exams, remember the absolute best way to solidify this extensive knowledge is through consistent, disciplined practice.
Exactly, that's the key. My sincere advice to all of you listening is, please revise this entire topic of hydrocarbons again before your exams. Focus intently on understanding the reaction mechanisms, the specific conditions required for each reaction, the regioselectivity rules like Markovnikov's, the reasons behind directive effects, and definitely the nomenclature and isomerism rules we discussed. Crucially, practice past year questions rigorously. Work through problems based on each lesson segment we covered today, preparation methods, reaction predictions, mechanism writing, isomer identification, naming. Pay special attention to the problem-solving approaches and common pitfalls we highlighted. And very importantly, if you encounter any doubts or points of confusion while studying this chapter, please feel free to reach out whether to your teachers, mentors, or study groups and get those doubts clarified immediately. Don't let them linger. Your strong and clear understanding of hydrocarbons is a vital stepping stone, a foundation, for excelling not just in organic chemistry, but in your entire competitive examination journey. Keep working hard.
A fantastic piece of advice to end on. This deep dive into hydrocarbons should definitely equip you with the detailed knowledge and, hopefully, the confidence needed to tackle this important unit in your exams. Thank you all for joining us on the deep dive, and keep learning.